So now we have a new test, the alternating series test. The alternating series test will be able to show us whether an alternating series is converging. It converges if the terms of the series are non-increasing, in other words, positive, right? Positive but maybe equal in magnitude for k greater than some index. In other words, we don't care about the beginning part again. And then the limit as k goes to infinity of a sub k is 0. That has to happen. Otherwise, it's divergent anyway. It would fail the divergence test. So I've got a lot of notes to write here. So this, it would be otherwise the series fails the divergence test. And that still holds the divergence test. You have to have the limit of your terms go to 0. If they don't go to 0, then you've got other problems. Okay, so if your limits of your terms go to something other than 0, always divergent, always. That's the divergence test, period. So it has to go to 0. But then there's a bunch of stuff going on in here, so let's look at it. So first thing is that it has to be greater than 0. Every term has to be greater than 0 once you get rid of the alternating part. So when you look at just the AK part, it has to be positive. And then it has to be non-increasing. Basically, has to be decreasing. So that's this portion right here. It has to be non-increasing. Right? You have to be going down in terms. Think of that alternating harmonic series and how they were going down. Right? That's what that's saying. So it has to be non-increasing. In other words, decreasing-ish. Right? So that's what non-increasing is. It's decreasing-ish. Right? They can be equal, but in general, there's a downward trend. And that downward trend has to be taking you to 0. And then it has to be taking you to 0, and it has to be non-increasing and positive after some index. In other words, again, we don't care about the first terms. If the first terms are a little wonky, that's okay. That happens. And so about the first few terms. If it goes up and then comes back down, that's all right. As long as it's coming back down, it's going to stay going down for the first few terms. It is very common that the first few terms are going up and doing weird things, and then we'll ignore them and look at the end, right? So that's what that's saying. And for the record, the whole k plus 1 thing is kind of arbitrary. In here, in this test, they write it as k plus 1, but it could be k, it could be k plus 2, it could be k plus 3. So k plus 1 is arbitrary. It could be k, k plus 1, k plus 2, k plus 3. It could alternate in a variety of ways. So don't think it has to be k plus 1. It's common that it's k plus 1, but it's not the only way to write these. Okay, so there's a lot going on. So k plus 1, kind of don't worry about that so much. Just as long as it's alternating, great. The term without the alternating part has to be positive and it has to be non-increasing. In other words, decreasing-ish. And at least as after the first few terms, right? So you have to be decreasing-ish after the first few terms. And it has to have a limit that goes to 0. If all of these things are true, then that alternating series converges, right? So if you have all of these properties for this series, it has to be positive, it has to be non-increasing, and it has to be, well, non-increasing after the first few terms, and the limit is 0. So if all of those things are true, then it's a convergent series. Cool. And the alternating series, of course, we've already learned that's a convergent series. It passes this test. All right, so now let's apply this test. So let me rewrite this so we can see it in the form that is written above in the problem, or in the theorem, I should say. So this is k equals 1 to infinity, negative 1 to the k plus 1, and 1 over k squared, right? Times 1 over k squared. So my a sub k is actually that part right there. This is a sub k, right? So step 1, I have to prove that a sub k is positive and non-increasing, right? I have to prove those things. So step 1. Positive and non-increasing. Well, nothing like a graph. Graph will work. So let's pull up a Desmos graph. All right, so to do this, I'm going to graph f of x equals 1 over x squared. Right, so, and of course, I'm only looking from x is greater than, or, well, greater than 1, greater than or equal to 1. Oops, sorry. X is greater than or equal to 1. There we go. There's a graph of it. You know what that is? That is positive because it is always above the x-axis, and it is decreasing because it is decreasing. That was a terrible window, so I had to make a better window. So I went 0 to 10 and 0 to 1 and then kind of zoomed a little bit. So that is what I'm going to graph on my paper to show that this is positive and increasing. So positive and decreasing. So it's positive, always above the x-axis. It is non-increasing because it is decreasing. Okay, so let me say that. So I'm going to graph from 0 to 10, 0 to 1. Of course, I have to give it scale to be a valid graph. And it was kind of going like this. And I graphed, oh, I don't really want to go to forever that way. I'll kind of go like that with a dot there. And so this is 1 over x squared. So that function is positive, check, right? It's always above the x-axis. And it is decreasing. Well, I guess I could just say it's non-increasing. Let's put it that way. It's actually a special kind of non-increasing, which is decreasing, which is more common for us to see, but there you have it. All right, those 2 bits are done. So I've proven that my terms are positive and non-increasing. Wonderful. Got those 2 bits. Now I just need to prove that the limit as of a sub k, prove the limit as k goes to infinity of a sub k is 0. Okay, here's where all the limit stuff that we learned is. So limit, oh, I'll do it in a different color. The limit as k goes to infinity of a sub k is the limit as k goes to infinity of 1 over k squared. And we learned a long time ago that anything over infinity is 0. Lovely. Therefore, since I have proven part 1 and I've proven part 2, therefore this series converges. Oop. I killed my whiteout. I just wanted to make that summation notation a little bit larger so it filled the whole thing. Not strictly necessary.